you for the kind introduction. Thank you for hosting us. So welcome everyone to this talk about deep learning for detection of extreme weather events. So this is a talk about a project at the intersection of machine learning and climate science that's been going on for about 1.5 years. So I'm Lukas. With me here today is André. I'm involved in this project and also lots of other people such as Ega and Leo who are also from ETH, and then various people from Berkeley Lab. I should say in the beginning that usually when we give talks about this, we have the luxury of bringing alongside a climate scientist from Berkeley. So we don't have this today. We're both computer scientists, not climate scientists, but still we'll make an effort to answer also questions regarding climate science as best as possible. Before we get to the actual contents, since most of you are students and since we get asked this a lot, here is one slide about how this project got started. So this project is actually coming out of another project that we did with the people here in the top left and other people that are not in this picture, where we take part in supercomputing competitions internationally. That means we go to various conferences about supercomputers, and we bring like a small supercomputer there, and we compete against other teams across various benchmarks and applications who can do them the fastest. And one of these conferences that we went to with these competitions was the International Supercomputing Conference in Frankfurt in 2019. And there we met some people from Berkeley Lab that were also part of judging this competition, and they were interested in working together, and so were we. And they brought up some climate science questions that we were able to tackle together with machine learning. Right, so what is this all about? So at the core, this project is about the detection of extreme weather events. So in order to understand this, first we need to know what are extreme weather events, why would we care about extreme weather events, and then how does machine learning come into play here. So what are extreme weather events? Extreme weather events is a very broad and vague term that covers various climate phenomena. One of these that we're going to reference to today is tropical cyclones. You can see an example of a tropical cyclone here in the top right. So tropical cyclone, again, is quite a broad and vague term for spinning masses of air that are typically high in moisture. And an example for a tropical cyclone is then a typhoon that you might can associate. And the second extreme weather event that we will reference today are atmospheric rivers. So you can see an example here. These are long bands that transport air that are typically high in moisture. And because they're high in moisture, also similar with the tropical cyclone, these events in particular are related to extreme weather events. So this is also why we care about extreme weather events, because they are related to real world effects such as floodings, or in other event cases also fires or droughts. And in order to be better prepared for these events and to protect them and analyze them, we care about extreme weather events. Now this particular project, as the title says, is about the detection of these extreme weather events, which is to be distinguished from predicting them across time. So what we're not doing is predicting when a tropical cyclone will happen in the future, but what we do is, given corpuses of data, we detect where certain extreme weather events are in the data. And this then enables other research, such as analyzing how do these extreme weather events form, how do they behave, how do they terminate, or perhaps other people that work on the prediction of these events, or also allows research such as if you take a climate scenario from today, and if you take a simulated climate scenario from the future, how do these extreme weather events are expected to change across these climate scenarios, for example, connected with what we want. Right, so this is the problem setting in which we're in. And before we jump into it and talk about how to apply machine learning to this, we should, of course, think about how was this done before. And how this was typically done before is that climate scientists created handcrafted heuristics. So you have to imagine that different climate scientists, individually or in small groups, they would sit down and they would write programs that are custom for specific events and with lots of like hard-coded parameters and that were meant for detecting these heuristics. And this comes with various downsides. I mean, one first downside is it has a lot of time of these people to create this, and often these are also very compute intensive. And then they are specific to event types. So usually, because you created one heuristic for one event type, you cannot quickly transport this to another event type. And lastly, there's quite limited agreement between these heuristics. So we saw earlier that these definitions of the events are very vague. And because they are so vague, the heuristics that people have built to identify these vaguely defined event types have very limited agreement between each other, which is of course problematic when you want to do science with it. And to really drive this point home, if you look at the typical definition of an atmospheric river, you see that there are all these adjectives here: long, narrow, transient, and then something about strong, horizontal, water vapor. So these are not precisely defined. And based on this definition, different people start creating different heuristics. They are not in agreement with each other. And this is really the problem that we set out to solve here. Given certain extreme weather events, how can we create a way to detect those that is fast, that transfers well to other event types, and that doesn't have all these biases that come into play when people call up heuristics. And the very fundamental approach that we took for this is that we had some experts, some climate science experts. They labeled a small set of data, more on that later, and then we regarded this problem as a semantic segmentation task and could apply techniques for machine learning there, which André will later share more light on. Okay, so first, before we now come to the machine learning methods, we need to know what's the data we're talking about. So most often in this project, we use Chem5 data. What does this mean? So Chem5 is a model for simulating climate data. It comes at a 25-kilometer resolution. That means it divides the Earth into these chunks of size 25 kilometers, and then it has 16 variables. So these variables are different channels, and each channel represents one input variable. So yeah, now maybe you're a bit confused because you don't have much climate science experience, and as you know, as computer scientists, as we are, we wondered, what does this really mean to us? And we can rethink of this, or we can get out of this model basically a picture that has a resolution of 1,152 times 768, and that has these 16 channels with different physics variables. So instead of having a typical picture that, let's say, has RGB, so 3 color channels, now we have these 16 channels where each channel represents one physics measurement type. And out of these 16, together with climate science expertise from Berkeley, we then picked 4 channels that are particularly relevant for the 3 event types that we set out to target first. So just to get a good understanding of what this data actually means, here's one picture. So this is one particular channel. So for every pixel, you have one floating point number, and the higher floating point number in this case means there's more moisture in the air at this location. And then now we can basically regard it as a picture just like we would with RGB data. If you don't believe that the Earth is flat and rectangular, you might be correctly noticing that there's a potential issue here, namely that around the poles, the pixels are way closer than at the equator. And while there are methods to tackle this, from spherical convolutions, in our case, this turned out to not be an issue. So we could actually regard this data as an image that has 4 channels, and instead of having RGB, as we have in other machine learning tasks, we have this 4 physical channels. And with this data, we could then set out and phrase our model as our task as a semantic segmentation task. And now André will talk more about, oh no, there's one more thing. Oh, right, so this was the input data. And then with these input data, we also needed labels, of course. And as mentioned earlier, we then had climate scientists sit down and with a custom tool that was appropriate for having these four physics input channels, they were drawing polygons corresponding to these events. So it's quite interesting here that we have like only 450-ish samples, which is very small in machine learning. So this is so it's quite remarkable that it was already possible to work with such samples, and this also brought some of the specific challenges with this problem. Okay, and now lastly, regarding the data, here's an example of various experts labeling the same timestamp. So they all got to see the same input data and labeled atmospheric rivers. These are these long and narrow things here, and tropical cyclones. These are these round blobs here. And as you can see, there's quite some agreement among the experts of where these events roughly are, but there is quite a lot of disagreement on where the boundary of the event is exactly. And this was then later also very important for choosing the metrics that we did, and also for how do we interpret the metrics that we looked at. Okay, and with this, now we have our problem set. We want to be able to detect these extreme weather events, specifically atmospheric rivers and tropical cyclones. We have selected 4 input channels, and we have these expert label matches. And now André will explain how we actually went ahead and applied machine learning.
Right. Thank you, Lukas. Yes, so I will run you through some of the things that we did here, and I'm going to gloss over some of the technical details, and if you are interested in more details, of course, you can ask about it afterwards, but of course I have to move a little bit fast for time reasons. So as we said, we're doing semantic segmentation, and if you start Googling around and look into how do I actually approach this kind of problem, you will find that there are lots of different things that you can do. There are lots of different benchmarks that people have proposed and looked at, and also lots of different models that sometimes perform well and sometimes don't perform well. And one of the most popular models that people use is DeepLab V3+. A lot of you might have already heard of this or even worked with it. It has been the state of the art for a long time. Right now, maybe there's some movement in the leaderboards, but it is a pretty solid model for doing semantic segmentation. It has pretty strong segmentation performance on a bunch of different tasks, obviously, but it's also a very complex model. That means it's pretty data hungry and slow to train and evaluate. And this is, of course, a problem for us because, as Lukas just mentioned, we have very limited data. So this, we worked with this model, and it worked reasonably well, but I'm not going to go into much more detail on this because we actually found a better alternative that works better for a data limited regime. I have one slide which is taken from the paper, but I'm not going to go into any detail right now of how this architecture actually works. If you're interested, maybe ask later. And so our alternative that we actually ended up using is a little bit less known. It's called CGNet. Came out roughly at the same time as DeepLab V3+, but is a very lightweight segmentation architecture that is designed for the deployment on mobile devices. So maybe you can't run DeepLab V3+ on your iPhone, but you can run this architecture on your iPhone. You can see on the right-hand side there's a graph of performances on the Cityscapes dataset, which is a popular benchmark for semantic segmentation. You can see here on the top performing pretty well, but also being very big, a very complex model with almost like 50 million parameters, DeepLab V3+, and then the CGNet has maybe around 2 orders of magnitude less parameters, but also performs a little bit worse than the DeepLab V3+. And again, here I have a slide about how this actually works, but I'm not going to go into detail. You can ask about it later. Another question is how do we train this? So now we've chosen the CGNet, and we can look into how do we actually estimate the parameters of our model. And in semantic segmentation, the cross-entropy loss is a commonly used loss. But of course, there's a big problem that is prevalent in semantic segmentation, that is class imbalance. I mean, basically everything is background, and the extreme weather events are only, a very small fraction of the data set. And of course, how people usually resolve this is weighted cross entropy. So you just kind of count the amount of occurrences of each class, invert that, and then weight your loss by this. But maybe there's some way that we can do better. In order to find a better way, we should maybe take a step back and look at what do we actually care about here. So what do we ultimately care about? So a common metric in semantic segmentation is the intersection over union, which measures the overlap and the union of your predicted mask and your ground truth mask. And of course, one idea would be, why don't we just directly optimize this? This of course doesn't work because it's not differentiable. But there's this thing called Jaccard loss, and you can maybe again ask me about this later. I'm not going to go into much detail, which approximates this IOU. And so we decided, okay, so we can optimize this Jaccard loss. So we did that for 15 epochs using the Adam optimizer. I mean, no surprise there. Basically, everybody uses Adam these days. And we convert at 59.3% training IOU and 56.1 test IOU, which is, our test set is temporarily after the training set, so there's no data contamination there. And of course, this might be a little bit underwhelming. It's like, well, I mean, those numbers are not that high, so is this all for nothing? Well, you might see now here, so this is an example actually of 0.59 IOU of two experts who have labeled the same time step. You can see they generally agree, but they don't agree on the boundaries. And as Lukas said, these boundaries just are inherently ambiguous. So actually having this kind of 0.5, 0.6 IOU is actually reasonable on this kind of data. So now for this end, I have this, so it's not working, so I also prepared it on YouTube. So here I have a video of how this actually looks. So the events are being tracked using a tracking heuristic that we added on top, and you can see, you can follow it, and you can see that it looks visually reasonable. All right, and now that means we're almost done now. Just real quick. So as Lukas said, we can compare different climate scenarios with this now. We can say, okay, we have this all-his climate scenario, which is kind of like the climate is today, and we have this unhappy climate scenario, which is under the assumption that climate change gets worse. And we can see that for artificial, for atmospheric rivers and tropical cyclones, the events that have a high precipitation get more likely under the higher climate change scenario. So this is of course a very significant result, and gives us something to think about. And also we have a map of places on the Earth where atmospheric rivers are more likely to occur. And these kinds of analyses are the things that we can use our models for. And now maybe just the discussion really quick. So one thing, of course, is we need more training data. That might either mean that we need more annotated ARs or TCs, because we have this limited data set, or even get labels for completely different kinds of events, and then we can, maybe move into a multitask learning setting, or just do more experiments with this. Another thing that we are thinking about is doing end-to-end tracking. Right now we have this tracking heuristic that we added on top to actually track single instances, and we can maybe talk about this later if anybody's interested. But of course this would be a thing for future work. And the thing that we're looking at right now is applying our methods to actual satellite observations, so actual real-world, real-time data. And of course new metrics, because as you might have noticed, there's some problems with inter-annotator agreement in our data. And yeah, thank you for listening to our talk, and I hope that you have some questions, and thanks.